magnetic circuits. Okay, so in electric circuits, what do we have? We have a potential that is supplied by some battery, right? So that we call as the electromotive force, EMF. Okay, and if there is a resistance R, then the current that is flowing, we take I. Okay, so if this EMF is given by V, right? So this is going to be V is equal to I times R. This is from the Ohm's law. So this is an electric circuit, right? Now what is a magnetic circuit? So if you take the electrical machines like transformer, motors, generators, they are called as the magnetic circuits. They involve the magnetic circuits. Okay, so why that is, we will see, because basically we can make an analogy between the electric circuits and the magnetic circuits. Okay, so instead of EMF in the magnetic circuits, there is something called as MMF, magnetomotive force. Okay, magnetomotive force. Now if you take a magnetic core like this, okay, and around it you are winding a coil, let us say. If current flows through this, then the current direction is going to be like this, right? Now what will be the direction of magnetic field that is induced because of this? In the coil, it is going to be induced in the clockwise sense, right? You can find it using the right hand rule. Okay, so you can visualize it like this coil, whatever is there, that is a kind of a EMF. Okay, in the electric circuit, just like V is creating a current, this current in the coil is the magnetomotive force, which is resulting in a flow of flux. Okay, of course the flow of flux and flow of current are a little different, but we can make an analogy like this. So you can write, because of the current flowing in the coil, a magnetic flux phi is produced. Okay, so this flux we can take as phi, right? A magnetic flux phi is produced in the core. This is the core. Okay, so magnetic flux phi is produced in the core, analogous to the current flowing in an electric circuit due to EMF. Okay, so this magnetomotive force MMF, this is represented as this. This is related to the current as N times I. Okay, so N is the number of turns, where N is the number of turns of the coil. Okay, so this is nothing but integral H bar dot dl bar, right, from the Ampere's law. The current that is enclosed is equal to the line integral H bar dot dl bar. So we have one analogy, we have two analogies in fact. One is the MMF phi is analogous to the EMF. Okay, and the what about the flux phi? This is analogous to the current. Now one more analogy is in the electric circuit. What did we see in the equation? V is equal to IR. In magnetic circuits, we have something called as reluctance. Okay, so this is represented like this. Okay, so this is analogous to the resistance R. Okay, now how this reluctance is related to the flux and MMF? Okay, so this is related as MMF is equal to the product of flux and reluctance. Okay, and reluctance, it is related to the physical dimensions of the core. Okay, so this is L by mu into A. Okay, where L is the mean length of the core. Okay, that means wherever the flux is flowing, right? For example, in this circuit, if you see, the flux is flowing along this path, this entire path, right. So, the mean length is going to be this entire circumference, okay. So, that is the length. And what is mu? Mu is the permeability of the core. And finally, A is the area of cross section of the core, okay. So, this is the first one, second, third, okay. So, these are all of magnetic circuits, and the other column is electric circuits, okay. Now, there are other terms as well. We have conductance, which is equal to the inverse of resistance, right. So, this is denoted by G. So, analogous to this conductance is permeance, and this is equal to the reciprocal of the reluctance, okay. So, now let us see what is the series connection, okay. In the series connection in electric circuit, if you see, the currents are going to be same and the voltages are going to be added up, okay. So, here also it is going to be something similar. For n number of magnetic circuit elements in series, the flux is going to be same through each of the magnetic circuit elements, okay. And what about the MMFs? They are all going to be added up, okay. So, the net MMF is equal to MMF1 plus MMF2 plus so on till MMFn, okay. So, this is for the series circuit. Similarly, we have for a parallel circuit, for n number of magnetic circuit elements in parallel, here the fluxes are going to be added up, okay. So, the net flux is equal to phi 1 plus phi 2 plus so on till phi n, okay. And the MMFs are all going to be equal. MMF1 is equal to MMF2 is equal to so on till MMFn. Now, what about the reluctances? Okay, so whenever they are connected in series or parallel, they will behave just like resistors. Okay, so if you take a magnetic core, something like this. Okay, so here what is present? There is an air gap here. Okay, so let us say the air gap is Lg. Okay, and the rest of the path mean length we will take as Lc. Okay, so the mean length of the core. Now, what is the equivalent reluctance that is offered to a coil which is wound in this manner? Okay, so what will happen to the flux? The flux is going to flow like this. It is going to complete a closed path in this manner. Okay, so in this path it is encountering an air gap as well. Okay, so in that case what will be the reluctance? So because of the core, the reluctance will be the length, the mean length of the core divided by the permeability of the core. That is important here. Permeability of the core, which is equal to mu r into mu naught. Right? Relative permeability into permeability of free space into the area of cross section. But in the path of the flux there is also the air gap. So this, because of the air gap, the reluctance is going to be the length of the air gap, so Lg, divided by, in the air gap it is free space, right? So what is the permeability? It is simply mu naught, okay, into the area of cross section, okay, because the area of cross section is going to be remaining the same. Okay, so the total reluctance here, the net reluctance is equal to the reluctance of core plus reluctance of the air gap. Okay, so basically you have to realize when the reluctances are in series and when the reluctances are in parallel.